All right, so let's go through the first couple of these for this. Okay, so the first thing we need to do is that we consider only the highest term, right? So for
Okay.
problem one, right, the highest degree term is n squared. The
Yeah.
3n, as n approaches really large numbers, the difference between n squared and n, right, is enormous, right?
Yeah.
Like even at just n is equal to 100 times 100 is 10,000 versus
hmm
300.
Three. Yeah.
That's a huge difference. So that's why we
hmm
discard everything below that. Okay.
So we would, I guess, for this one, you discard plus
Yeah.
two would just be
Yeah.
gone,
And so in this
and
case,
okay, go ahead.
just because it we write O of n squared. Okay.
hmm
O of n squared, because n squared is the biggest term. Not only that, okay, but if it was 3n squared plus 3n plus 2, we would still write n squared. Because what we're describing here is because to put it in nice, easy layman terms for people who do mathematics but don't want to make it their life,
Yeah.
which is most computer scientists, to be honest.
Yeah.
We're just describing what we're simply writing down what the shape of the curve is, right? N squared
Yeah.
is the shape of that curve versus O of n, which would look like a straight line, which looks like a straight line, assuming I
Yeah.
can draw a straight line, which I can. So anyway, for the next one, right? We just that's just reminding you, oh yeah, FOIL's a thing, right? First in or out or last, right? So this
hmm
would be um so n times n squared would be n to the fourth, right? And then it would also be, and then we would do outer, which would be n squared times pi. So wait a second, that's just n squared. So that's less than n4, so I don't care. N times n squared,
Yeah.
that's n to the third, I don't care. So in other words, it's only the first two big ones that matter. So it's O of n to the fourth, right? You put O of n around it.
And that would be
We're gonna
so
skip.
write the corresponding. So
Mhm.
I guess that would be, I guess, for the biggest big O time complexity, we're not necessarily writing what you're writing, kind of that O of n squared would be
O
kind
of
of
n
what we're looking
squared or O of n to the
to the
fourth.
fourth.
Now in this
Yeah, I get
now
okay.
in this course, okay, there are four. So while this document goes over a bunch of runtimes, in this course specifically, there are only 5 runtimes. There's only 5 big O's we'll ever use, and we're only going
Mhm.
to use 3 of them for a bit until we get to then we'll add another one when we get to recursion, and another one when we get to trees. So sorry, another one when we get to sorting. My bad. Okay, the
So
three that
we're
we currently are working on, the 3 that we currently care about, as we go into array lists and as we've worked with linked lists, are O of 1, O of n, and O of n squared. Right?
yeah.
O of 1 means it takes the same amount of time no matter how many items we have. O of n
Yep.
says we do an operation for each item or some operations for each item. And then O of n squared says for each item, I'm going to do something. I'm going to compare that item to each other item, or for each item, I got to look at every item in the list. Okay.
hmm
So something like the isUnique function will be O of n squared. Okay.
Okay.
For the way we currently write it. Okay.
And I guess so
Moving on, we're
for
going
the
to,
second one, you got rid of, just so I'm thinking correctly, you combined the two
yep.
n to the second powers
Yep. I
and
multiplied it
essentially
out.
discarded
Mm-hmm.
plus n and plus pi divided by two.
Mm-hmm. All right. Now, yeah, we just discarded all that stuff because we didn't need it because it's not the biggest term. All right, we're
Yeah.
gonna skip 3 and 4 for a second. Okay.
Okay.
If we'll actually come back to this last because that's actually one that's a doozy. Okay.
That's what I was thinking of, because that's a little tricky for that 3-1. I was like,
This one, this one was when I wrote this, it was again during the summer I have to always adjust the curriculum, but I don't like to adjust the homeworks. So for this one, these have formulas applied to them. These are actually something that you typically do in calculus 2, where they're
okay.
what they're called convergences. but we don't really
Mhm.
care about those right now. Just know that there's a formula for it, and I'll show it to you in a minute. Okay, so
Okay.
this is 10, so 10. T of n is equal to 10. That
Mhm.
is just O of 1 because it's constant
That's
time.
kind of what I thought it would be.
Now,
Just because there's no, it's a constant
right,
in
exactly.
my head.
O of 1 means constant. It's a constant time. It's constantly this. It doesn't matter what n is. Another one, 8. Let's skip down to 8. Okay.
Mhm.
Okay.
Okay.
12 log n versus n squared versus n over 2, right? That's just simply misordered to confuse you. It's the biggest term in there is O of n because O of n is much bigger than log n, right? Again, to draw a really bad graph, this is O of n and this is log n. You can write the shape of log n is the
Oh,
parabola that's lying on its side. That's the shape of log n. Okay.
so
And also
log n
log
is
n is
kind of like,
small.
yeah.
So, just an aside, your teachers most likely taught you how to do logarithms wrong. Logarithms, or at least logarithms wrong for computer science, which is,
Mhm.
and also logarithms wrong for practical use, I should say. They
Mhm.
they probably went into detail. They probably talked about this relationship between the exponent and the base and the whatnot. No. Log something if something is log base 2 of n, okay, what does that mean? That means that I can split n in half a certain, that's going to tell me how many times it can split n in half, okay? That's what it's going to do. So in other words, log base 2 of 32, right? Now, the normal way you might figure that out is, okay, that's equal to 5 because 2 to the 5th is equal to 32. But you're right. But no, the way
Mhm.
we do this, you can figure that out is 32 is, we can split 32 into 2 16s. We can split those 16s into 8s. I can take those 8s and split them into 4s. I can take those 4s and split them into 2s and 2s into 1s. And after that, I can't split it up any further, right? So
Yeah.
32, so how many splits is that? That is 1 split, 2 splits, 3 splits, 4 splits, 5.
Yeah, 5.
So that's that's what logarithms are. And by the way, the same thing applies for like log base 10. You're just splitting it up into how many times can I split it into tenths?
Mhm.
So 8, 9, 10. Oh, I can split it up into 10 tens, and I can split up the tens into 10 ones. Now, obviously, this falls a bit apart when we're dealing with like, things that don't, like log base 2 of 33. But that's close to 32. And the next number up would
Yeah.
be 64 for that. So it's just a little bit more than 5. But in terms of being able to visualize that for computer science, that's what you need to know. Okay.
Hmm.
The last thing to know here is that here n and log n are multiplied together. Okay. I mentioned that there's 3 runtimes that we'll be talking about. Sorry, there's 3 runtimes now
Uh-huh.
for this class, right? And the other 2 we'll be learning about and this is in the order in which they are from fastest time to slowest time. Log n and O of n log n. This is when we are basically doing basically a binary search. That's log n time when it basically, what that represents is basically our choice. We're every time we're sifting through a bunch of items, and each step we discard half the items to look at, which is useful. And
And that's O of log n,
yep, O of log
right?
n. And n log n is divide and conquer time, which is a recursive
Mhm.
strategy, which we learn more about in higher level or algorithms class. But it's the way that the best sorting algorithms we have work.
Mhm.
Dividing it up into smaller problems and then conquering those small problems. All right, now going back to this. This one is actually called the triangular number sequence. Okay, which means,
Mhm.
and that converges to n times n plus 1 over 2. So while it looks like it is just O of n because it's got a single n in it. It's
Mhm.
n plus n, sorry, it's n times n plus 1 over 2. Now, in 2168, I typically go over how to prove this by proof by induction. But instead, I'll just leave you with a kind of a visual understanding, not a proof, not a formal proof, just an understanding, right? Here's 1, here's 2, here's 3, here's 4, and
Yeah.
I'll go down to 5, which creates we're creating a triangle here, right?
Yeah.
And a triangle is slightly more than half the square,
Mhm.
right? And that's what we get over here, right? If we had a square, right, of side n, of each side n, the area would be n squared, right?
Yeah.
And here we're getting this is n squared plus n over 2. Okay, so that's slightly more than half the square, which is what we see this my bad drawing is. So that's why this is n squared. Visually, that's why it's n squared over 2. But that's what this formula is, 1 plus 2. And the reason I bother putting it on the sheet and to begin with is that this is very, very common in computer science, specifically the other way around. For the first item, I compare it to n other items. For the second item, I compare it to n minus 1 items. To the third item, I compare it to n minus 2 items. And for the next item, I compare it to n minus 4, and then n minus 5, n minus 6, and so on and so forth. Right? That's why we have that one. So it's n, so that's n times n plus 1. Right? And so you just multiply that out to get your big O time. Similarly, for this one, this is a formula. Just look up to solve that one, look up the formula in Google for 1 squared plus 2 squared plus 3 squared, right? All the way to n squared, right? And it will have a similar formula. You just look up that formula to figure out what that is. Okay.
And that was, and number 3 felt like it was similar to what your module video went over. You kind of drew that out. I have that kind of in my notes as
Oh,
well.
wonderful. I made those videos so long ago that for sometimes I forget what I put in them. All right, let me go ahead and go through these other problems very briefly. Okay, and then I need to step away for a second. I'll come right back. So let me go through. Let me just go and make sure. Right. So these operations will basically tell you how it works with an array list. And most of the operations on an array list are going to be the operations that take place inside an array list are either constant time or linear time. Right. They either they involve going through basically all the items or half the items in the list, or you just simply add an item to the end or remove an item to the end. That's how an array list works. Okay.
How do you want the answers? Would you say for like number 1?
I would say
Would you want?
you would either, so for number 1, to get an item, so how much time does that take?
I mean, I thought it was constant time.
Yes. So you can, so I would accept either, that's correct. I would either accept, so either writing O of 1, that's an acceptable answer. Writing constant is also, the constant time is also an acceptable answer. Both are acceptable because they mean the same thing. Everybody in computer science knows that those are the same things, right? Similarly, if it was O of n time, if an answer was O of n time, if you wrote linear time instead, everybody knows. So that's fine. I'm not picky. I'm not pedantic about it, Right. Oh yeah, I remember this one. I never put in the old, okay, whatever. This one is fine. Yeah, okay. And then Bogosort. So this one talks about time complexity for this algorithm, and it also talks about space complexity, okay? Right, space complexity is you can measure everything in terms of the input size. So this says, given your input size, your limit, how much space is this algorithm going to use compared to the input size? Okay, and that's also in big O notation. For this one, insertion sort, that's kind of a hint when I tell you what it is. You can look up popular sorting algorithms. In fact, for Bogosort, you should look up Bogosort. So Bogosort is one of two sorting algorithms, Bogosort and Stooge sort, that exist only for pedagogical reasons. What does that mean? That means they only exist inside an algorithm class. Nobody actually creates these and runs them for real, because they're terrible algorithms. BOGO sort has a runtime of, well, you'll figure that out. You can look it up on Wikipedia. Wikipedia is great for sorting algorithms, by the way. It's the best for finding out about sorting algorithms. Okay.
Mhm.
Stooge sort has a runtime of like I think it's like n to the 2.7. Sorry, it's n to the 2.7. It's a weird runtime, and that you have to calculate using the what's called the master theorem. Okay, but basically what we care about is worst case runtime and average case. And the best way I can say that is that this is and my hint here for you is that with a worst case runtime, what we're considering here is the algorithm for BOGO sort simply says you shuffle, like you're trying, assume you've got a deck of cards. Here you're trying to sort your deck of cards by randomly shuffling, okay? So if you shuffle it, now if you're just simply shuffling it, there's no guarantee that you don't end up with the same sequence more than once, right?
Yeah.
Right. So that's what I'm saying over here. What if I could hit the same examples, the same thing multiple times? What would be the worst case scenario? And what's your explanation for that? For the average runtime, instead, what you want to consider is what's called kind of a deterministic viewpoint, that each permutation of cards could only be hit once. Does that make sense? Right? You can only do each permutation once. Whereas in worst case, you could do each permutation an unlimited number of times. And for the worst case scenario, you should be obnoxious with that definition of unlimited in your answer. Utterly obnoxious, okay, for the correct answer. For the average, you can only hit each one. So you're trying to figure, in that case, you're asking, how many permutations does a deck of cards have?
Yeah.
And so that will get
Makes
you
sense.
to the answer.
Hmm.
Again, the answer is available on Wikipedia, so you can look it up. Okay.
Okay.
And I highly recommend going into Wikipedia to look it up and reading up the explanation for why those are. But again, BOGO sort exists simply solely for the purpose of being a terrible sorting algorithm.
Is that what, I guess, what would the, is that for, would the use of that be for, I guess, comparing what you have to, I guess, the worst? I guess what would be the
use of
usage of
BOGO
it?
sort is just simply to have a fun sorting algorithm that runs at this really bad runtime, right?
Hmm.
Okay, because the runtime it runs at is distinctive, right? What we're looking at, so there's right, so right, you have n to the dth power, and you can get that d to be arbitrarily large, but there's a couple of worse. There's some really bad runtimes. Okay, one of the worst runtimes you can get is instead c to the nth power, where n is your input size, right? So in other words, something like 2 to the n. That means your workload doubles for every extra item you have. But there's a worse runtime even beyond that. Okay. That's kind of the idea here. There's a worse time beyond that. And that's what BOGO sort is.
Oh. Wow. So it's worse than doubling every time.
It's worse than doubling every time. Worse than doubling every time. Okay.
Interesting, I guess. Why, I don't know why someone would create, I guess, the usage of it, I guess. Why someone...
because there's a couple of different problems where the only solution is something of that runtime, like the traveling salesperson problem, where basically you have where you're trying to visit 5 different cities, each with a major airport, okay, and you want to find the cheapest itinerary between these 5 cities, okay, and then you expand that to n. And the only possible way to figure that out, essentially, or rather the naive way to figure that out, which is close to the best, unfortunately, that we have is to literally check every single one of the possible routes that you could take.
Oh,
The cheapest one. So you check all of those. Okay, you check all permutations.
oh, that does make sense.
So this one, again, the reason we create bad runtimes is also because for bogus sort because it's hilarious. Bogus sort's hilarious. The entire idea of basically trying to sort a deck of cards by playing 52 pickup. Okay. That's what this is. Okay. So give me 1 second. I'm gonna step out for a second and I'll be right back. And I'm
Okay.
gonna stop recording here. Be right back.